So classification of matter. Scientists like to put things into categories. It helps us to organize our thinking. Things can be classified in multiple ways. If you think about vehicles, you can classify them different ways, right? You could look at cars and say, well, this is a hatchback, and this is a four-door sedan, and this is a two-door coupe. You could classify cars that way. Or you could say, well, this one runs on gasoline, and this one's electric. Or you could go by color, or by overall size. So there's lots of different ways you can classify things, and that happens in science as well. So we classify matter. First of all, what is matter? Not what is the matter, but what is matter? So matter is anything that occupies space and has mass. Your textbook, your desk, your chair, your body, all composed of matter. The air is composed of matter. Air occupies space, right? It's not obvious that it has mass, but it does. A specific instance of matter is called a substance. So, this pencil could be called a substance. Water is a substance. It's a particular kind of matter. So we can classify by the state, the physical form. Is it a liquid? Is it a solid? Or we can classify it by the composition. What are the things that are making it up? What are the atoms and molecules doing? So the states of matter. The three states of matter that we will be concerned with in this class are solid, liquid, and gas. So if you take a solid and you heat it up, it will melt into a liquid, and if you heat the liquid, it will go into the gas state. And the difference between these three states has to do with the freedom of movement of the particles and how far away they are from each other. In the solid, the particles are touchingly close, and they are in fixed positions. So these guys are not going to be moving. And so right now, you guys are in the solid state of students. You're all sitting down. You're not moving relative to each other. In the liquid state, the particles are still close together, but now it's kind of like they're swimming around. They're moving around, milling about. So in lab, we put the stools away and people are walking around, and it's like water. Everybody's moving. We're still close together, though. The gas state is when there's a big distance between the particles. They are free to move, and there's a lot of space. And this is when class is out, and everybody diffuses out the door and spreads out, and you just go off on your own directions. That's the gas state. That's what the particles are doing. So I described that, and then we'll go through these fairly quickly. Solid matter packed close together in fixed locations. So the particles vibrate. It's not that they're completely still. They do vibrate, but they don't move around past each other. So are you guys perfectly still right now? No. I think everyone's at least breathing, right? Some people are taking notes, nodding their heads, fidgeting, whatever. That's fine. You're moving. That's like the vibration of the particles in the solid. Oops. That'll work. So fixed volume, rigid shape, characteristics of a solid. Think about an ice cube. Take the ice cube out of its tray. Does its shape change? No. Put it on the counter? No. Put it in a cup? No. The shape stays the same. That's a rigid shape. And the volume is fixed. It doesn't change. The volume doesn't change. We can categorize solids by how the particles are arranged. The solids may be crystalline, meaning they're arranged in a three-dimensional pattern. Diamond is an example of this. There is a definite order to the carbon atoms in the diamond. That's a crystalline solid. The other type is amorphous. The prefix a means without, and morph refers to shape. So without shape. There's no long-range order. So part of the class is crystalline, because, you know, there's 5 of you on each side of the bench, but then we have a little bit of an amorphous situation going on in the back corner and up here, where it's less regular. In a liquid, we still have things close together, but free to move around. So liquids are characterized by a fixed volume, still close together, but not a fixed shape. Not. Think of a cup of water. If you take a cup of water in a measuring cup and you pour it into a big dish, does its shape change? Yeah, it spreads out to fill the bottom of whatever container you're putting it into. Does its volume change? No, the volume's the same. Gaseous matter. Here the particles have a lot of space between them, and they are free to move. So gases can be compressed. Here we have an illustration of a solid. We have all these particles very close together. If you try to compress this in a piston, it's not going to compress. These are already as close together as they can be. And you can put pressure on them and it's not going to change. In a gas, because there's a lot of empty space, if you put pressure on the gas, you can cause those particles to squeeze in closer together. So gases are compressible. There's a couple things I think are missing from this. So gases have variable shape. They will actually expand to fill their container. I mean, they will take on the shape of the container, and they also have a variable volume. They will expand to fill the container, and you can compress them and make them smaller. So solids, fixed shape, fixed volume. Liquids, fixed volume, variable shape. A gas, variable shape and variable volume. There will be a test question. So that's classifying matter by its state, its physical state. We can also look at it according to its composition. And this is an overview. We've got, here's matter. Is the composition variable? If no, then that's a pure substance. And under pure substances, can we separate it into simpler substances? No, that's an element. Yes, we have a compound. If the composition is variable, that means we have a mixture. Is the mixture uniform? If no, it's heterogeneous. If yes, it's homogeneous. So we'll talk about all of those. The first division is between a pure substance and a mixture. So a pure substance is made up of only one component, and the composition is always the same. In a mixture, you have 2 or more components, and the proportions can vary. This is tedious. So there I drew 2 water molecules. In water, all of the individual particles are the same. Each particle contains 2 hydrogen atoms, 1 oxygen atom. Always, always, always. That's what water is. If you change the particles, it's not water anymore. You can also have a mixture of hydrogen and oxygen. So we'll explain why later, but hydrogen and oxygen make molecules with themselves. And so if you have a mixture of hydrogen gas and oxygen gas, there are 2 different types of particles. These two things contain the same number of hydrogen and oxygen atoms, but they are very different. Here we have a mixture of gases that if you light a match to it will explode dramatically. Here, same atoms arranged differently. This is water, which we use to put out fires. This is a fixed composition. This is variable. I could put a little more hydrogen in or a little more oxygen in. Here, I can't add just a little bit of oxygen because each of the particles is fixed. Any questions about that? Those pure substances we categorize into two types, elements and compounds. And this has to do with whether you can break them down, separate them, decompose them into simpler substances. So if we look at water, we use water as an example a lot. Water can be taken apart into oxygen and hydrogen atoms. We can take them apart into a simpler substance. If you look at something like, I don't know, what would be a good example? Say, copper metal. So copper metal is just a bunch of copper atoms next to each other. Oops, they're supposed to all be the same size. If I cut this in half, is it a simpler substance? No, it's still just copper atoms. So this is an element. It's only one kind of atom. This is a compound. There's more than one kind of atom. If I separate the different types of atoms, then it becomes a simpler substance. So elements cannot be chemically broken down into simpler substances. These are the basic building blocks of matter. These are like the individual Lego bricks. They are composed of a single type of atom, such as helium. The helium gas in a helium balloon is just helium atoms. There aren't any other kinds of atoms in there. A compound contains two or more elements that are put together in a fixed proportion, a definite proportion. So water is two elements, hydrogen and oxygen, put together in a fixed proportion. One oxygen, two hydrogens. Hydrogen peroxide is two oxygens, two hydrogens. The proportion is different, and so the substance is different. The compound is different. Most elements are chemically reactive, and so they don't just sit around as the elements. They will combine with other elements and form compounds. Hydrogen and oxygen gases, you can put those two together in a balloon and all's fine until there's a spark. And then kaboom, there's a chemical reaction in which the hydrogen and oxygen combine to form water. Water is a compound and it's much more stable. So any questions about elements and compounds, pure substances? The other half of that chart was mixtures. Mixtures can be divided into heterogeneous and homogeneous. Oops, didn't mean to do that. So a mixture has two or more components, and the prefixes here help us understand what these words mean. Heterogeneous, hetero is a prefix meaning different, and homo is a prefix meaning the same. So homogeneous means that this mixture is the same throughout. Heterogeneous means that there's different things in it. You can see different layers, or there's chunks or lumps or something. There's pockets of one thing within the other. So the categorization is based on how uniformly the substances mix. Heterogeneous mixture, we've got multiple substances and their presence can be seen. So if we mix salt and sand together, I think we can all imagine that. If you took some salt from the salt shaker and some sand from a sandbox and you mixed them together, you can still see the salt crystals and the little sand particles, right? You can mix them and shake them up and you can still see the individual pieces. That's a heterogeneous mixture. Okay? Another example would be oil and water. Put some oil in a bottle, put some water in a bottle, put the lid on, shake it up, mix it as hard as you can, set it down. What happens? The oil comes to the top and the water goes to the bottom. It separates all by itself. The top of that liquid has, the oil part has different characteristics than the water below it. There are two distinct parts. It's a heterogeneous mixture. In a homogeneous mixture, there are multiple substances, but it appears to be a single substance. And if you look at the top, the bottom, the inside, the outside, they all have the same composition and properties. An example from real life is sweetened tea. In the South, they call this sweet tea. You take a cup of tea and you put some sugar in it and you stir it up, and the sugar seems to disappear, right? But it mixes. It mixes homogeneously with the tea. And so if you were to sample the top of the tea and the bottom of the tea, it would taste the same. It would have the same amount of sweetness, right? What if you put sand in your tea? Stir it up. Would the same thing happen? No. The sand will not mix homogeneously with the tea. It'll settle out on the bottom and make a heterogeneous mixture. Mixtures, one of the things that makes them distinct from compounds is that you can separate a mixture into its components without doing any chemical reactions. And you do that based on differences in physical and chemical properties of the two substances involved. And this could be a homogeneous mixture or a heterogeneous mixture. There are lots of different techniques to do this, and developing new techniques for separating mixtures is a big part of chemistry. So we've got these things all mixed together. Maybe you have a sample of human blood and you want to pull a specific antigen or something out of it. How do you separate that? Well, you have to look at the individual components and identify differences in their properties, and then exploit those differences. So we've mentioned sand and water. So you've got sand in the water. How can you separate that? Well, if you wait until all the sand settles to the bottom, you can carefully pour the water off the top. That's called decanting. That's our fancy chemistry word for that. You pour the water off the top and the sand will stay behind. You're exploiting the difference between the sand being a solid and more dense than the water being fluid and able to pour out. When you have a homogeneous mixture of liquids, say alcohol and water, you can't separate these by decanting because there aren't two layers. They're uniformly mixed together. But the two liquids probably have different boiling points. Ethanol has a much lower boiling point than water does. So you can use what's called distillation. So here's your mixture, say of alcohol and water, and you heat this up. The alcohol has a lower boiling point. It will boil first and go into the gas state. Now, if you want to keep the alcohol, which is usually what people are trying to get when they're distilling things, you're going to make it run through this condensing tube. It's a double-walled tube with water running in between the layers to cool it and make it condense again. But it's condensing over here, and so it's going to run down here, and you can collect it in another flask. You can keep doing that until pretty much all you have left here is water, and over here you have alcohol. And you've separated the two liquids based on differences in boiling points. Volatile is a term we use to mean that it's easily vaporizable. It evaporates easily, goes into the gas state easily. Another method is filtration. This is a method that you use in the kitchen. If you have an insoluble solid and a liquid, you can separate them by filtering. A filter is going to have holes, pores that are small enough that the solid can't go through, but large enough that the liquid can. So here's a more chemistry example. Here we've got a glass funnel. There's a piece of filter paper here. Paper is porous and will allow the water to go through. The water comes through here, but it'll catch any solids that are present. This is basically what's happening when you make coffee. There's a coffee filter, right? The hot water and the coffee grounds get mixed together, and then you want to separate the grounds from the coffee because nobody likes the gritty coffee grounds when they take a swig of coffee. So you run it through a piece of paper, a filter. The nice coffee comes through and the grounds stay behind and you throw them out. You make spaghetti.
This would be an example of separating heterogeneous.
Yes, exactly. This is an example of separating a heterogeneous mixture. Making spaghetti. You boil the spaghetti in the water, now you have to separate it from the water. You use a colander. Why don't we use filter paper? Well, the spaghetti is bigger than the coffee grounds, right? And so a colander is basically a bowl with a bunch of holes in it, right? The holes are small enough that the spaghetti won't go through, but they're much larger than the pores in the coffee filter, and so the water goes through much more quickly. So you just pour it through the colander, the water goes through, and you catch the spaghetti. In that instance, you're interested in the solid. When you're making coffee, you're interested in the liquid. Any questions?